Hello, welcome to my talk on local and global statistics for point sequences. It's a beautiful sunny day here in Graz, Austria, but still I wish I could be in Lumini at Serum Research Center in the beautiful surroundings. Unfortunately, this is not possible right now. Unfortunately, we cannot meet personally right now. I hope we can do that soon again in Lumini or some other places. So here I want to speak about some of my recent work. That's joint work with Mark Münch and Daniel Elbaz, who both work here as postdocs at TU Graz. So the point is to speak a bit about global versus local statistics for point sequences. So global here means uniform distribution. So the setting is the following. We have a point sequence yn of points in the unit interval. And as you all know, this is called equidistributed or uniformly distributed modulo 1. This is uniformly distributed mod 1 if the number of points, the relative number of points of the sequence in some test interval if this converges to the length of the test interval, and if this is the case for all test intervals. So here this is for all a between 0 and 1. This is a theory that has a long tradition going back more than 100 years. Some of the very classical results here are that the sequence of fractional parts n alpha, this is uniformly distributed mod 1, provided that alpha is irrational. And the fundamental theorem of Weyl says that this is also true if you take higher powers of n. So if you have n to the d alpha for some positive integer d, or in general if you have some polynomial at integers, at positive integers multiplied with alpha, if you take fractional parts of this, this is also uniformly distributed mod 1 whenever alpha is irrational. And you probably also know that there is a way how you can easily check uniform distribution and how you can efficiently analytically figure out if a sequence is uniformly distributed or not. This is the famous Weyl criterion. Which says that you can consider exponential sums e to the 2 pi I j yn if this tends to 0 for all integers j which are not 0. If this is the case, then you do have uniform distribution modulo 1. So this is a global theory in the sense that you keep your test window fixed. The test window or the test interval here is the same size essentially as the full interval, so you keep it fixed. And the reason, so the fact that you keep this test interval fixed, this is responsible for the fact that here in this Fourier analytic criterion, you can treat every frequency at a time, so one frequency at a time. So the j's here are the Fourier frequencies. When you expand this indicator function into the Fourier series, but you can do this individually for fixed values of j, one after another. For every fixed value, you need to check this criterion, but you don't need anything like uniformity in j to apply this Weyl criterion. And for comparison, I will also tell you about the metric theory of this. So here for these particular sequences, you can easily figure out for which alpha exactly this is uniformly distributed mod 1 and for which alpha it is not. If you plug in some general sequence here, say some an, sequence of distinct integers, then typically you cannot easily determine anymore for which particular alpha this is uniformly distributed mod 1, so this can be very difficult to check. Say, for example, if an is 2 to the n, it's very difficult to figure out if for some alpha this is uniformly distributed or not, this sequence here. But the metric theory says that this is uniformly distributed mod 1 for Lebesgue almost all alpha. So in the sense of Lebesgue measure, uniform distribution is the typical behavior for almost all alpha, independent of whatever the sequence an is. Whatever the sequence an is, some sequence of distinct integers, you always get uniform distribution for almost all such alphas. And that's very easy to prove. That's something also Weil did, even if he didn't like, at the time of writing his paper, he didn't like results that contain an unspecified measure zero set, because that was in his period when he was a follower of constructivist mathematics. So this is obviously a non-constructive result. You cannot figure out what the exceptional set is, but the exceptional set always has measure zero. So the point is, this metric theory here is very simple. Whatever the sequence an is, an alpha, fractional parts of this, is always uniformly distributed for almost all alpha. It's very, very simple. So now we switch to the local statistics. What's that? So I said, I understand this here is a global statistic. It always keeps the view at the full picture, at full scale. The local statistic that we're studying here, statistics, is the pair correlation statistic. So that's just one possible local statistic that you can consider. There are many others, but this one is defined in the following way. So you have your sequence yn of points in the unit interval, and then you count the number of pairs. Which are close to each other at scale roughly 1 over n. And then you ask if this converges to the expected value in some sense. So here, obviously, if you count this, if you believe that this should show some sort of random behavior, then of course this should converge to the length of the interval. Here random behavior would be, well, this one you can choose. The test window has length 2s over n. So this one you can choose. Then you have essentially n other choices for this. The length of the test window is 2s over n. So you will see on average, you might expect to see 2s other indices here, which are so close to this fixed point. You have n choices here, you normalize with n, so the random thing to happen would be that this converges to 2s. This is for all s. And if this happens, you will say that the sequence yn has Poissonian pair correlation. So this pair correlation is just one example of a local test statistic. You could also study what is called triple correlation, quadruple correlation, higher correlations, where you don't count pairs of elements of the sequence close to each other, but where you count triples, so 3 points which are close to each other on this scale of roughly 1 over n. And one thing that's particularly interesting is if you count the gaps between the elements of the sequence in sorted in increasing order. So if you fix some capital N, you have some y1 up to y capital N. Typically, they are not sorted in increasing order, but you might reorder them in the increasing order, and then take a statistic of the gaps of this sorted sequence. So that would be called distribution of level spacings. That's something which is interesting for people in theoretical physics, where this percolation business originally comes from. But working with this ordered sequence is analytically very unpleasant. So typically, it's not possible to do that analytically because this ordering procedure is just very complicated. So if you think about what you're doing here, if you think about this in terms of exponential sums, as in the Weyl criterion, then these differences here, so you have some exponential sum with these differences here, this is realized essentially as a modulus squared of some exponential sum. And this can be treated quite efficiently analytically, but if you want to bring in additionally the correct ordering of the points here, mod 1, this can be very complicated, and in general there's no analytic machinery to do that efficiently. So the pair correlation in this sense is the easiest local statistics. If you cannot do the pair correlation, then you're unlikely to be able to handle triple correlation, quadruple correlation, or level spacings or other things. So I should also emphasize that the average spacing, so we have n points, all in the unit interval, the average spacing is roughly 1 over n. So these test windows, they are roughly of the same size as the average spacing in our sequence of points. So this is a very localized statistic. In a way, this is the highest localization you can reasonably talk about. So if you try to put some higher power here, instead of n, you try to put n squares or something, then you will not see any pairs or any interesting things happen anymore. So this is really the most local you can go in this sense. So this is the most global picture you can take. This is the most local picture. Of course, you could also do something in between, but here today we do this. Now what do we have? N alpha mod 1. So for this Poissonian pair correlation, I will write PPC. So Poissonian pair correlation means that this expression converges to this. And in this setup, Poissonian pair correlation is pseudo-random behavior. Okay, I don't tell you why it's called Poissonian, but I tell you if this sequence of points behaves with respect to this test statistic randomly, then this is called Poissonian behavior, and the correlation is called Poissonian. So N alpha mod 1, it turns out that this does not have Poissonian pair correlation for any alpha. So whatever alpha is, never ever do you see Poissonian pair correlation. So we see it's possible that the sequence has uniform distribution, but does not have Poissonian pair correlation. This could happen. Now let's take a higher power. Let's take n to the d alpha. Well, let's just start with n squared alpha. Does this have Poissonian pair correlation or not? Well, the situation is unclear. We don't know the answer. So it's conjectured that if alpha does not allow approximations by rationals which are too good in the sense of their phantom approximation, so if alpha is, say, a quadratic irrational, which is difficult to approximate by fractions, then the conjecture is that this should have Poissonian behavior, should have Poissonian pair correlation, but it's not known. So we don't have any results about specific alphas. As far as I know, we don't know any explicit natural constant alpha here for which we could prove that the sequence has Poissonian pair correlation. So it's unclear, but there is a general metric result of Rudnick and Sarnak. Something like 20 years old, which says numerically for almost all alpha, this does have Poissonian pair correlation. And the result remains the same if you don't have squares but higher powers. So if you take n to the d times alpha, d is 2, 3, 4, something else. We don't know about specific values of alpha, we cannot do that. But the metric result still holds. For almost all alpha, such a sequence has Poisson percolation. Not if the exponent is 1, so not for n times alpha, this is a special situation. But if we have second or higher power, then we do see Poisson percolation. And you might wonder, where does it come from? Why for this sequence coming from a linear sequence, why do we not see Poisson percolation? And here, why do we see Poisson percolation? You can interpret this in terms of continued fractions, but I will show you later a straightforward criterion which allows you to see what's going on here. So I said in equidistribution theory, the metric theory is very simple. Whatever sequence you start with, an, you always have uniform distribution mode 1 for almost all alpha. Here it's different, obviously it's more complicated. If we start with this sequence, we don't have Poisson percolation for almost all, or actually for any alpha, but if we start with this one, with exponent d bigger than 2, then we do have Poisson percolation for almost all alpha. So obviously some arithmetic property of the sequence an must play a role here. And it turns out that this sort of thing is very strongly controlled by what is called the additive energy. So together with Gerhard Lacher and Mark Luco, we proved the following. So if we start with some integer sequence an, if this satisfies that the additive energy, I will tell you in a moment what it is of order, let me write it like this, is of order 3 minus an epsilon, epsilon is positive. Whatever positive epsilon you can save here, then the sequence an alpha has Poisson percolation for almost all alpha. And there's a counterpart. If an has additive energy too large, then the opposite is true, so then it does not have. This sequence here does not have Poisson percolation for almost all alpha, so then the conclusion here is not true. Then we do not have Poisson percolation for almost all alpha. So if you have a sequence of distinct integers, then n cubed, so first let me tell you what the additive energy is. The additive energy of the first n elements of the sequence discounts the number of solutions, n1, n2, n3, n4, indices up to capital N, such that an1 plus an2 equals an3 plus an4. So in a way, this counts the number of representations of some integer as a sum of two elements of your sequence. So I guess you can see that if you write some function, I don't know, r of m is the number of representations of m as a sum, or you can also rewrite this into a difference, let's say as a difference of two elements of the sequence up to index capital N. So if you write Rn for this number of representations, then this additive energy just sums up the squares of this number of representations, right? So you see, if you have a certain number of representations, you can use them here, you can use them there. In total, you get the square of the number of representations of a fixed integer, and then you sum these over all integers. And you also see how large can that be. If these are all distinct integers, you always get the diagonal contribution, so you always get at least n squared solutions, and you get at most n cubed solutions, because this you can choose. And then if everything is distinct integers, you have at most one choice for this. So the maximal order this can have is n cubed. And so the criterion here, it tells you if you can save a little bit, over the trivial estimate, then you do have Poissonian percolation for almost all alpha. If the additive energy is of maximal possible order, then it's not true that you have Poissonian percolation for almost all alpha. And you can easily calculate what the additive energy is for this sequence. It is of maximal possible order, so the order is essentially n cubed. So in this sense, it's no surprise, if you know this general criterion, it's no surprise that here this sequence fails to have Poissonian percolation for almost all alpha. And for these other sequences, for these polynomials, it's also known, so the number of representations of integers as differences of polynomials, this is quite well understood. The additive energy is almost of smallest possible order if the degree here is 2 or more. So the additive energy is very small. We can apply the first criterion over there. We do get Poissonian percolation for almost all alpha. So let me try to tell you where this additive energy comes from. So we try to prove a metric result. If you want to prove metric results, what you always do is you estimate or you calculate expectations and you calculate variances. Then you try to apply Chebyshev's inequality and the Borel-Cantelli lemma, and then you're done if everything works out. So we have to estimate first and second moments. So we integrate. We try to get a metric result in alpha. We integrate this counting function. And this usually is not problematic, so we can do that. And then we also try to estimate the second moment. So let me write, instead of this 1, let me write an I for the same indicator function, but normalized in such a way that it has the average 0. So we subtract the integral from the indicator function so that the average of the indicator function is 0 instead of 2s over n. And then the variance is the square integral of this. And the key point is to control this variance, to give an upper bound for this, in order to be able to apply Chebyshev's inequality and the Borel-Cantelli lemma. Now we try to expand this into a Fourier series in the spirit of Weil's criterion. So this indicator function we convert this into a Fourier series. There's a coefficient Cj and some e to the 2 pi I jx. And now we don't want to have an infinite Fourier series. We don't need the zeroth Fourier coefficient because we have subtracted it. And how large do we have to go up with our Fourier frequencies? Well, so the function here is localized at scale 1 over n essentially. So we need Fourier coefficients going at least up to n and a bit higher, then we can approximate the function, the indicator function, efficiently by the Fourier series. So we need to go up with this j to capital N and actually a bit higher, and then this trigonometric polynomial is a good approximation for this function here. And now you see this is different from the Weil criterions, and the Weil criterion for uniform distribution, the test window, the test interval was fixed. We could treat all Fourier frequencies individually, one at a time. In the Weil criterion, you fix the frequency and then you run the Weil criterion. Here we cannot do it because in the test window, the test function is localized. So this is on a very small scale, and because of that, we have to treat all the Fourier frequencies simultaneously. We cannot just do them one by one, but we have to do all of them at the same time. And that's what is causing some extra problems here. So these coefficients, we can imagine them to be of size roughly, in absolute value, roughly 1 over n. So if we continue our calculation of the variance from here, then we plug in, instead of the function, we plug in the Fourier series. We estimate the coefficients, they are roughly 1 over n. We multiply out. We get an integral of trigonometric functions. We use orthogonality of the trigonometric system, and then it turns out this translates into a counting problem of counting. So these j's go up to n. We have a square, so we will see 2 of these. Essentially up to n. Let me cheat a bit here and there. Then I'm doing this all wrong, I'm sorry for that. So here I should have written from the very beginning fractional parts of am alpha minus an alpha. So here actually what we see is counting am alpha minus an alpha, fractional parts of this. Sorry. So we have pairs here, fractional part of am alpha minus fractional part of an alpha. We can bring the am and the an together. So it's am minus an in brackets times alpha, fractional part of this. If we square, then out of these 2 indices, we get 4 indices. So it's n1, n2, n3, n4, at most n, at most capital N. And then we count if J1 an1 minus an2 minus J2 an3 minus an4 if this is 0. So what we have done here is we have approximated the indicator function by a trigonometric polynomial we have squared out. We use the orthogonality of the trigonometric system, so when we integrate here, then we only see a contribution if this whole expression here is 0. These are the only things that contribute to the variance, and now we have to count these. So how do we count that efficiently? Well, you see, essentially, if we could treat every Fourier frequency one at a time, then this would be very easy, because then these here could both be fixed. Say, maybe we could even make them equal after applying some Cauchy-Schwarz. So this would essentially disappear, and we are left with the question whether this minus this here is 0, and this would be more or less the additive energy. So you see this, if I wouldn't have these two coefficients here extra, I could bring that to the right-hand side, and I would count representations as differences of elements of the sequence, and that's exactly the additive energy. But additionally, we have these extra indices here, and we need to have them because they come from the fact that we have a localized test function, and that we need all these frequencies simultaneously in the Fourier series. So we cannot just ignore all these coefficients, J1 and J2, and all the possible values that they can have, but we have to take that into consideration. So let's try to take this into consideration. So what we're counting here is let me write maybe V for this difference here and W for this difference here. So we're trying to count, I bring this to the other side and I divide by that. So we're trying to count if J1 V over J2 W is 1. So let's assume that we have fixed V and W. Now we're trying to count how often this is 1 when we take a summation over these possible values of J1 and J2. And interestingly, at this point, we can bring in the Riemann zeta function. And we need the Riemann zeta function on the half line. So let's think of this as being essentially, for our purpose, a summation over, well, let me also write J here, up to something, 1 over J to the 1/2 plus IT. Then we can use this in our counting problem. Let's define some auxiliary function p of t. This is a summation of all integers m that can be represented as a difference of two elements of our sequence an. And then we take here the number of representations of m up to index n as a difference of elements of our sequence. So this counts. The number of representations of m in the form an1 minus an2, where both indices go up to capital N at most, times m to the it. And now, if we multiply the square of this against the Riemann zeta function on the half line, so we multiply this auxiliary function with the Riemann zeta function, take a square, modulo square of this, and integrate. Then what we see is, so we just try to multiply out here. There's an integration. I square this. So here I get a summation. Let me write this as v and w again. V and w. We get representations of v, representations of w. Then we get v to the it, w to the minus it. So that comes from squaring this. And then we get, if we believe that really the zeta function has such an expression, then we get a summation j1, j2. One over square root j1, j2 times j1 to the it here and j2 to the it here in the denominator. So here, this is an j1 v over j2 w to the it. And the punchline is, if this quotient is 1, then we see a large contribution to the integral. So you see this, if this quotient is 1, then this is 1 to the it, which is still 1, so it's always constant 1, and we're taking a summation, some numbers, constant function 1, some other numbers, and we're integrating this over some range which I didn't specify yet. So this is a large contribution, and in contrast, if this is not 1, so if this j1v over j2w is not 1, let's say it's bounded away from 1, then we see a small contribution to the integral. Because if this is not 1, then this is an oscillating function, so it's something different from 1 to the it, so that's an exponential function which is oscillating. If we can control the size of this oscillation, then we can know that if the integration range is long enough, then these oscillations help us to control the size of the contribution to the integral, and this will be small. So of course I'm lying here in all points that I'm saying. So the Riemann zeta function of the half-line is not equal to something like this. I didn't specify how long I want to take a summation here. If I want to relate this to the counting problem, I would need to sum up to capital N here. I didn't specify where I'm integrating. I didn't tell you what I want to do with these coefficients here, this square J1, J2. But the key point is that if I start with this counting problem, I'm trying to count the number of solutions of this. I can interpret this as trying to count the number of solutions of this. And this is in some way visible in this integral formula that I'm writing here. So if this has many solutions, where this quotient is equal 1, then this integral is large. And if there are not many solutions where this quotient is 1, then the integral is small. And I pretend that all the errors I make here, I can just throw them away, and I can efficiently estimate the number of solutions of this differential equation that I'm trying to understand. I'm claiming that I can control this in terms of such an integral if I do everything a bit more carefully. So I have to specify where I'm integrating. Actually, I need some extra integration kernels and all sorts of things. But this is very roughly what happens. If I can do that, if I can really interpret this as the number of solutions in the counting problem that I'm trying to understand, then maybe I'm very lucky that having this interpretation in this form translates into such a thing. And then here I can, of course, try to estimate this expression with something I know about the Riemann zeta function, right? So once I'm here, I start with this counting problem. I can pretend that I can find this counting problem in some way or the other inside here. Once I'm here, I can go back here. And now, if I know how large the Riemann zeta function on the half-line is, if I know how large, say, the square integral of this function p is, I can try to control efficiently how large this can be. So what's the square integral of this? Well, it has something to do with the number of, with the summation over the square of the number of representations. That's what I want to see. This will be the additive energy, right? So the square of this will, after some Cauchy-Schwarz, essentially be the summation of the squares of this number of representations, which will be exactly the additive energy, so that will be nice. And I just have to find a way analytically how to work with this zeta function here. And what's the whole point of everything? What I'm trying to do here, the whole point of the whole thing is I'm trying to get rid of these coefficients here that come from the Fourier frequencies. I try to go back to an interpretation with the Riemann zeta function to splitting these two things. One estimate for the zeta function is square integral of this. The square integral of this is the number of the sum of the squares of the number of representations here, which is the additive energy, which is the same thing without J1 and J2. So the whole thing, the whole point is I try to get rid of the influence of these Fourier coefficients here that I have to treat simultaneously, and by this zeta function argument, I can get rid of these J1, J2s, and I can go back to the similar quantity where I don't need to take a summation over J1, J2s, but where I can take both of them being equal 1, so that so that I only see the additive energy, which is easier to calculate. So of course I could try to, if I start with some sequence AN, I can try to estimate this directly, but it's very unpleasant, it's very complicated to estimate it. If I run this argument, I only need to estimate the additive energy. This is usually much easier, and in particular for many sequences, the additive energy is known. The order of the additive energy is either known exactly, or there are good upper bounds for that. So finally, let me tell you what I've been recently doing with Mark Munch and Daniel Elbaz. So everything here that I said here starts with AN being a sequence of distinct integers. Now, let's try to start instead with a sequence of reals. And the leading example for us here always was when xn is n to some power theta, theta non-integer, bigger than 1. So maybe you believe me that in such a setup, we don't need to count number of solutions of Diophantine equations anymore, but we need to count. So the A's are x's now. This is xn1, xn2, xn3, xn4. Instead, we need to count solutions to Diophantine inequalities. So this is the equation that controls the variance now. Observe that in the integer case, it's exactly the same. So in the integer case, if some expression in integers is smaller than 1 in absolute value, then it is equal 0, obviously. In the real case, there's difference. We can run a similar argument here. It's a bit tricky because now this will not be exactly 1 anymore because we don't have exact equality here. So this will only be very close to 1, and then this will not be equal 1, but it will be bounded away from 1, and then technically you run into all sorts of problems, and it's very unpleasant to do this, but together with Mark and Daniel, we try to pull through with that. What is really interesting is the following. What's really interesting from my perspective is the following. So in the real number setting for the sequence xn, in the end you relate everything, this percolation business, this metric percolation problems, you relate it to a generalized additive energy, which is counting the number of solutions n1, n2, n3, n4 up to capital N, for which an1 minus an2 plus an3, sorry, these are x's now, xn1 minus xn2 plus xn3 minus xn4 is smaller than 1 in absolute value. And you can establish a criterion which tells you if this is not too large, you do have Poissonian percolation for almost all alpha of the sequence x and alpha. If this is too large, then you have the opposite. But the interesting thing that happens now is that you can introduce a new parameter here, gamma. Gamma between 0 and 1. And here you count solutions that are particularly close to 0. And it turns out that solutions of this inequality for small alpha, for small gamma, meaning gamma close to 0, are worse than solutions for larger gamma. So what means small, what means large? Small means, say, gamma equal 1 over n or 1 over square root of n. Such a solution is worse analytically than a solution for, say, gamma 1/2 or 1/4. The reason is that in the end here, in this counting problem, we multiply with something, and if we have a solution for something small here on the right-hand side, we can multiply with something large here and still stay below 1. So in this sense, the solution for small gamma, they cause more problems analytically than the solutions for large gamma. And this, of course, is an effect that you do not see in the integer setup. So if everything is integers, if this is an integer sequence, then here you can see, well, if it's smaller than 1, it can only be 0. It cannot be anything else. So in a sense, this is a pathological case where all solutions that you count at all, everything is always a solution for small gamma, because always the solutions you count are for gamma equals 0. And in the real number case, this is not so clear anymore. So maybe heuristically, you might hope that the solutions have some degree of uniformity, some degree of regularity in gamma, so that the solutions up to gamma here should be roughly of order gamma times solutions with 1 on the right-hand side. So this modified additive energy, looking for solutions for something small, close to 0, should be much less when gamma is small than the full additive energy. And this will help you because having few solutions of that will allow you to save something in the analytic argument and to establish Poissonian percolation for a large class of sequences that you start with. And the point is, this is something that is totally new in the real number setup. So if you start with integer sequences, you cannot see anything like this because, as I said, every solution for something smaller than 1 is a solution for gamma equals 0, or not arbitrarily close to 0. So you don't see any regularity of this type at all. But for real sequences, if you believe that your sequence is reasonably well behaved, if you believe there is a sort of small scale regularity in the number of solutions to these equations up there, then you can deduce small scale regularity of x and alpha with respect to percolations. And I find it very interesting. So I end with an open problem. So n to the theta times alpha fractional parts of this has Poissonian percolation for almost all alpha when theta is bigger than 1. This is established in my most recent paper with Daniel Elbaz and Mark Münch. this uses exactly this sort of small-scale regularity, then we know that the same sequence does not have Poissonian pair correlation for any alpha when theta equal 1. And in this interpretation here, the reason is, well, because the difference is between n to the theta for something bigger than 1 or n to the 1, the difference is that here we only see integers, and here we see other things also, and here we do have this small-scale regularity in the number of solutions, which for integers we don't have. And we believe, we conjecture, when theta is smaller than 1, then we should have Poissonian pair correlation for almost all alpha. Of this sequence again, it is known that such a small-scale regularity in the number of solutions holds again when theta is smaller than 1. So really theta equal 1 is an exceptional case here because everything is integers. Now if theta is smaller than 1, and of course still positive, then we don't have an integer sequence again. We do have this small-scale regularity, but unfortunately we run into analytic trouble with our zeta function argument. This is all I wanted to present here. Thank you very much for watching and listening. I hope you're all doing well. I hope you all stay healthy. And I hope that we meet in person sooner or later again, either in Lumini or somewhere else for a glass of wine or a glass of beer. You are very much invited to be my guest for such a glass of wine or beer. Thanks again. Goodbye.